right. The next section we will spend quite a bit of time on. We're talking about the definite integral now. So we will spend probably like 5 days-ish on this section. And then once we finish this section, we'll do our next test, which is actually going to only cover 3 sections. The 2 you just took the quiz over and this. So trying to do a test over a smaller chunk of material before we move into the next piece. So first we have, it's like a lot of these sections start out, a lot of background information. We have been doing these limits when we are finding areas, right? We've talked about estimating area under a curve, and then we said if we want the true area under the curve, we have to do the limit as that number of rectangles goes to infinity. We've also talked about similar things when we're talking about distance. We were looking at, if we had velocity, going backwards would give us the distance traveled. We can see this in a lot of different ways, and it actually has another name for it. What we've been doing when we do the limit of the sums of the areas of those rectangles, that's what's called a definite integral. Okay. We are going to spend pretty much the rest of the semester talking about this integral idea. So it's that really skinny looking tall S here. It's saying it starts at A and ends at B. And all it means is that area under the curve, the limit of those rectangles like we've been looking at. So notation wise, the f of x, the thing we are integrating, is called the integrand. The a and b are the limits of integration. We call a the lower limit and b the upper limit. This is all one symbol. Okay, you can't just have a dx by itself. And in general, anytime you have this integral, we have to have a dx on the end. When we're working these, if the integral goes away, the dx goes away. So that integral and the dx are all part of the same symbol. You can't have one without the other. All right, so your book, I just put some of the pictures out here to show you. Just like we've been talking about, we can do areas under the curves. Now, everything we've been looking at, we were talking about curves like this, where we had a definite starting and stopping point and everything was above the axis. But that's not always the case. We can have curves that dip below the axis. And in that case, anything above is actually a positive area, below is a negative area. So if I integrated this entire thing, you would get like the net change. We would have the positives, we'd subtract off the things underneath and get an overall net change between the two. Okay. So this theorem tells us that we can do the integral anytime we have a continuous function. So any polynomial we can do the integral of. Rational functions, when we have asymptotes, those are a little more tricky because they have a discontinuity in them. So we'll talk about what to do in those situations eventually, but for now we're going to be looking at nice continuous functions and evaluating the integral for those. So this is what we have been using. We've talked about the change in x and the x sub i's. We were doing that on the quiz. We did that on the last problem that we just discussed. The integral just has your a and b are your starting and stopping points from that interval that you're given in the problem. The f of x is the equation itself. So we'll evaluate some of these today the same way as we were doing before. We will also just work on writing an integral to match a problem, and that's really probably all we'll get through today. So use Riemann sums to evaluate this. The Riemann sum is that big sigma, the summation notation that we have been doing. So this is just like the last question on the quiz, except I'm asking it a different way. I didn't say find the area under the curve x cubed minus 2x on the interval 0 to 4 using limits. I'm just giving you this and expecting you to know how to get there. So our process is the same. We need our change in x. So our change in x is our ending, which is the top number, minus your beginning, divided by n. So that's just a 4 over n. Your x sub I is your starting, which is the lower one. So we started at 0, plus the change in x was 4 over n times I. And we just get a 4 over n I. So now we're going to do the limit as n goes to infinity of the sum from I equals 1 to n of your f of x sub I times the change in x. That's what we said the integral was equal to right here. So I gave you this, I'm just rewriting it in this notation. That's just the same thing we were doing. F of x sub I is taking this and plugging it in to your equation. Every x gets replaced with the 4 over n I. So we have 4 over n I cubed minus 2 times 4 over n I. This dx is really just like your change in x. So times the change in x, which was 4 over n. So far, so good. Now we start simplifying this. We're not going to do the limit until the very end, so we have to work with the sum first. We definitely want to clean this up as much as we can. Can I cube and distribute my 4 over n at the same time? That's going to confuse you. So 4 to the third would be 64 times my other 4 would give me what? 256. Oops. N to the third times n would be n to the fourth, and that's an I cubed. Minus 2 times 4 times 4, so 32 over n squared I. Okay, so I multiplied everything out. You guys okay there? Now we use our summation formula. So once you use the summation formula, that sum goes away. So the I cubed formula is n squared times n plus 1 squared over 4. The I formula is n times n plus 1 over 2. cancel and n squared. 256 divided by 4 is 64. So that will give me 64, if I FOIL that, n squared plus 2n plus 1 over n squared. 32 divided by 2 is 16. I can cancel an n. If I'm doing too much in one step, let me know. I'm going to go ahead and distribute and simplify. So 64 n squared over n squared would be a 64. 128 n over n squared would be 128 over n. 64 over n squared. Distribute a negative 16 here. So negative 16n over n is negative 16 minus 16 over n. Can we do the limit now? Yeah. Everything with an n on the bottom turns into 0. So you get 64 minus 16. So our final answer is 48. So same thing we ended section 5.1 with, just giving you a different notation to start your problem. I'm asking the question in a different way, but it's the same calculations to get there. Questions on that? The next one, I'm not asking you to calculate anything. I just am asking you to write an integral. So take this limit and write it as an integral. So your integral symbol is that tall, skinny s. Whenever you have that, you have to have a dx on the end. Okay? What would my limits be? The bottom number should be negative 3, the starting point of your interval, and it ends at 2. Okay. This right here gives us our function. Now you might see a lot of different things on that x. You might see something like 2xi, or like I gave you I minus 1. You might even see something like m, which we'll talk about in a second, which represents a midpoint. It doesn't matter. This x thing, I don't care what the subscript is. Those i's, that's referring to if you're doing a left hand, a right hand, or in a minute we're going to talk about a midpoint sum. It doesn't matter. When you write the integral, all of those just turn back into an x. So it's just 2 minus 3x. And then that change in x just represents your dx. So here's our integral. The integral from negative 3 to 2 of 2 minus 3x dx. That's going to be like the first 5 questions on your homework. Well, not doing any calculations, you're just taking the way I asked you the question yesterday and writing it and how I would ask you the question today. Just going back and forth between those notations. Let's practice evaluating another one. So first we need the change in x. How do I get it? 5 minus 2 over n, so 3 over n. Then we need the x sub I. How do I get that? 2 plus 3 over n I. Or we started at 2 this time, so it's not going to be quite as pretty since we didn't start at 0. Okay, now we write it in the limit form. So the limit is n goes to infinity of the sum from 1 to n. Then we are plugging in here. So we have 3. X is turning into the 2 plus 3 over n I squared plus 4. And in place of the dx, what do we put? the change in x, which was 3 over n. Okay, so we have a lot of simplifying to do here. I have to distribute my 3 over n. So that would give me a 9 over n times, if I FOIL that parenthesis, that would be a 4. It's 12 over n I plus 9 over n squared I squared. So I distributed the 3 over n and I squared my parenthesis in that step. So now if we distribute, we get 36 over n plus 108 over n squared I plus 81 over n cubed I squared plus the 12 over n. I realize this is a lot of work. Have I lost anyone? You have a couple options. You do have some like terms, the first and last one, if you wanted to add those together. Or you could skip right to the summation formula. So either way, I'll just go ahead and do the summation. 36 over n, it doesn't have an I with it, so it's a constant. So when you add it up, what do? Times n. 36 over n times n. Okay, the formula for I is n times n plus 1 over 2. Formula for I squared is n times n plus 1 times 2n plus 1 over 6. And 12 over n would just be multiplied by n. The n's would cancel on the first and last term, so you're left with 36 plus 12, so that's a 48. Here I can cancel an n. 108 divided by 2 is 54. So if I distribute, I get 54n over n, which is 54, plus 54 over n. Okay, am I doing too much at once? Keep going. So here I can cancel one of these n's. If I FOIL this, I would get 2n squared plus 3n plus 1. So if I distribute, I get 162n squared over 6n squared. So what does that reduce to? 27. Okay. 81 times 3n over 6n squared. So that would be 81 over 2n. (81 over 6n squared), or you can change that to a 27 over 2n squared. Now if n goes to infinity, everything with an n on the bottom disappears, so we get 48 plus 54 plus 27, which is 129. Okay, obviously these get incredibly ugly, right? So we're really hoping that maybe in the next couple days I give you a shorter way of going about them. But for now, you don't appreciate the shortcuts if you don't have to do it the long way. So we're going to do this for one more day before we talk about any other ways of working it, okay? I want you guys to try example 5. You're not actually calculating anything, you're writing the integral on this one. So it'd be the limit, or the integral from 0 to pi. In this, I don't care what kind of variable I have, just change it to an x. So it's x cubed plus x sine of x. And what do you replace that change in x with? Dx. Alright. Let's go ahead. Let's see how far we can get today. Okay, let's talk about, do you want me to keep going or do you want me to stop? Stop? Okay. So it's one assignment for the 2 days. We have to still talk about the midpoint rule. So tomorrow, I'm going to do the midpoint rule and all the examples that go with it. And then you'll be responsible for